Okay, welcome back, dear students, to the tutorial about the group theory. This is the sixth video. In the last two videos, we had discussed about the construction of character table of various point groups. And today in this video, we are going to discuss about the reduction of a reducible representation. Okay, and we also will discuss the direct product. Okay, first we are going to discuss about reduction of a reducible representation into irreducible representation. We know that representations are two types: reducible representation and irreducible representation. We know that irreducible representations are more important. That is a very characteristic property of a point group, and that also represents many properties of the molecule, its wave function, its spectroscopic transition, etc. Depends on the irreducible representation, like that. That is very important. And sometimes we have a reducible representation. We want to reduce into irreducible representation. Okay, in the conventional way, we already did that in the earlier classes. That is, how can we reduce into a reducible representation to irreducible representation? What was the conventional way? It was to similarity transform that reducible representation into block factored matrices. Okay, by similarity transformation, it is converted into block factored matrices along the diagonal, and each of the small block factored matrices belongs to an irreducible representation. That was the conventional method. Now we are dealing with a simpler and more easy way how to reduce a reducible representation. Okay, you have to know that the character of a matrix is unchanged by similarity transformation. Okay, during similarity transformation, character cannot change. For example, I will show you. Okay, that is, if we suppose A is a reducible representation, and we are, by a suitable similarity transformation, it is block factored into another matrix. Okay, it is block factored diagonally. That is, it is A1 dash, A2 dash. Suppose it also, the third block may be similar to the A1 dash, and this is also A1 similar to A1 dash. Suppose this block may be similar. This is A2 dash and this is A3 dash, like that. And each of these A1 dash, A2 dash, etc. are irreducible representation. Suppose. Okay. Then according to our rule of similarity transformation, during similarity transformation, the character of the matrices do not change. That is, character of this matrix, the original matrix, chi A, okay, is equal to character of this matrix. That is, suppose I am writing this A dash. Okay, so chi A is equal to chi A dash. And chi A dash is equal to sum of the characters of all these diagonally block factored matrices. And these diagonally block factored matrices are IRs, irreducible representation. So we can write here chi R, that is character of the reducible representation, is equal to sigma I AI chi IR. Okay, that is, suppose the like this, that is character of A1 dash plus A2, character of A2 dash plus character of A1 dash. A1 dash is coming here 3 times. So AI into, so 3 into character of A1 dash. And A2 dash coming here 2 times. 2 into character of A2 dash, like that. So we can write chi R is equal to sigma I AI chi IR. And that is given here. That is, we can write chi R is equal to sigma Aj I'm using J or I, anything we can use, AJ, chi JR. Okay, that is character of the reducible representation is equal to sum of the characters of the irreducible representation. Okay, simple. For AJ is the number of times the block constituting the jth IR will appear. Okay, number of times the jth IR is present. That is simply AJ. Okay, understood. And chi JR is the jth irreducible representation. Sum over all the IR. We get chi of the reducible representation because character of matrix is unchanged by similarity transformation. And suppose we are doing a mathematics here. Multiply both sides by chi IR. That is, in this equation, we are multiplying both sides by chi IR. That is, here we are multiplying chi IR. Here also we are multiplying chi IR and sum over all the operation. That is sigma R. So we get sigma R chi IR chi R. Chi IR is a irreducible representation. Chi R is reducible representation. Here also multiply with chi IR and sum over all the operation chi R. So we get like this. That is sigma R chi IR is equal to sigma R sigma J into AI chi JR into chi IR. AJ into chi JR into chi IR. Simply multiplying chi IR here and chi IR and sum over all the operation. And here we are rearranging the summation. So the order of summation is not a matter. So we can write sigma J first, then sigma R AI into chi JR into chi IR. Take this part. That is sigma R AI into chi JR into chi IR. We can take AI outside. So AI outside sigma R into chi JR chi IR. Can you remember this equation? This is the great orthogonality theorem and this is equal to H delta Ij. AI already here. This AI is here. It is equal to H into delta Ij. And this is equal to, we studied that this delta Ij is equal to 0 when I not equal to j. And delta Ij is equal to 1 when I is equal to j. So this equation will vanish or this equation will 0 when I not equal to 0. I not equal to j. So according to orthogonality theorem, only I equal to j can survive. From this equation, only I equal to j can survive. So only I is equal to j can survive. So in that case, we can write this is equal to AI into h. Delta Ij become 1. Okay, that is when I is equal to j, and that is the only surviving combination. I not equal to j becomes 0. So when I equal to j, this become delta Ij become 1. So this term, that is this term is equal to h. So a into h. So we can try this is equal to, that is sigma r chi r into chi I r is equal to h into ai. Delta Ij is equal to 1 when I is equal to j. Okay, that is only surviving combination. So therefore we can write AI is equal to 1 by h into sigma chi r chi IR. This is the very important equation that is called reduction formula. Okay, and what is this equation means? Here what is AI? AI is the number of times ith irreducible representation present in the given irreducible representation. We are going to reduce a reducible representation. For AI is the number of times the ith IR is present in that reducible representation is equal to 1 by h. H is the order of the group. Sigma, sum over all the operations, sigma r should be here. Chi r into chi IR. What is chi r? Chi r is the character of the rth operation in the reducible representation. And chi IR is the same the character of the same rth operation in the ith irreducible representation. Okay, can you understand? Chi r is the character of the reducible representation. Chi IR is the character of the irreducible representation. It's a very important equation. Using this equation, we can reduce a reduced representation, reducible representation into an irreducible representation. From this equation, we can find number of times the ith IR is present in a given reducible representation. You will understand this more clear by taking an example. Suppose I am taking C3V character table, C3V point group. Okay, we have already discussed the character table of C3V, and this is the character table of C3V. Okay, this contains 3 IR, A1, A2 and E. Okay, there are 3 IR in C3V. Gamma A is not a IR. Gamma A is a reducible representation. I am going to reduce using reduction formula. It is an example. It is an example for a reducible representation we are taking to do the problem. Okay, so gamma A 5, 2, minus 1, that is a reducible representation. A1, A2 and E are the irreducible representation. Only 3, because there are 3 classes, only 3 IR is present. Okay, what was our formula? Our formula is this. That is AI is equal to 1 by H into sigma R chi R into chi IR, where H is the order of the group, chi R is the character of reducible representation, chi IR is the character of irreducible representation. First, we are going to determine number of times the A1 IR irreducible representation present in gamma A, the given reducible representation. Okay, what is equation? 1 by H is for C3V character table, C3V point group, H is equal to order of the group is equal to 6 into sigma, sum over all the operation. So we are taking a bracket here. Chi R. What is chi R? Before that, there are only one element in this class, E. So 1 into chi R, that is 5, character of the reducible representation, into chi IR, which irreducible representation we are considering A1. So chi IR is 1 into 1 plus. Next, we are summing over all the operation. First we are taking E, then next C3. There are 2 C3, so 2 into character of reducible representation 2 into irreducible representation 1. Okay, plus next sigma V 3 into minus 1 here and 1 here in the A1 into 1, and that is equal to 1 by 6 into 5 plus 2 into 2 4 plus 3 into minus 1 into minus 1, that is equal to minus 3. That is 9 minus 3 is equal to 6. 6 by 6 is equal to 1. So A1 is present in only 1 times in gamma A. Okay, next we are going to determine number of times the A2 IR is present in gamma A. Okay, so we can write again 1 by 6 into. Okay, again we are considering A2. First E. E only 1, so 1 into character of gamma A 5 into character of A2 in E is equal to 1 plus again C3 2 into character of gamma A reducible representation 2, character of A2 is 1 plus again 3, sigma V is 3 here, so 3 into here minus 1 into here minus 1, and that is equal to 1 by 6 into 5 plus 4 minus 1 minus plus minus into minus plus 3 that is equal to 9 plus 3 12 by 6 is equal to 2. So number of times A2 present in gamma is 2 and number of times A1 present is 1. N A1, this is N A2. Okay, next N third IR E. We have to consider all the IR. Okay, N E. Yes. again 1 by 6 into, okay, 1 into 5 into 2, 1 into 5 into 2, plus 2 into 2 into minus 1, 2 into 2 into minus 1, plus 3 into minus 1 into 0, and that is equal to 0. And that is equal to 1 by 6 into 5 plus 5 into 2, that is 10, 10 minus 4, 10 minus 4, 6, that is equal to 1. Okay, that is we can write gamma A, the reducible representation, can be reduced into A1, A2, E, that is 1 time A1, that is A1 plus A2 2 times is present in gamma A. So we can write 2A2 plus 1 into E. So E is present in 1 time, so E. So that is the reduction of gamma A, a reducible representation gamma A. Actually it consists of 4 IR, A1 and 2A2 and E. Understand? Okay. Suppose we take another example, gamma B, an reducible representation gamma B. Gamma A we already converted. Gamma A is equal to A1 plus 2A2 plus E. We already reduced it. Now another example, gamma B. 7, 1 and minus 3 are the characters. So our reduction formula is AI is equal to 1 by H into sigma R chi R chi I R. Okay, so first we are finding the number of times A1 present in gamma B. N A1 is equal to again E only 1 time, so before that 1 by H, that is 1 by 6. Order of the C3V point group is 6. 1 by 6 into 1 into character of the reducible representation 7 into character of the IR A1, we are considering A1, therefore here 1. That is the first element. Second element C3. There are 2 C3, so 2 into character of gamma B reducible representation, that is 1 plus character of C3, character of C3 in A1, that is 1 plus again 3 into 3 sigma V is here, minus 3 into it is 1. Okay, and that is equal to 1 by 6 into 7 plus 2 minus 9. Okay, that is equal to 0. So A1 is not present in gamma B. Okay, so next number of times A2 is present in gamma B. Okay, we can check very easily. Again 1 by 6 into 1 into A2, 1 into gamma A, 5 here. So 1 into 1 into 7 is equal to 7 plus again next C3, 2 into 2, 4, 4 into 1, 4 plus 3 into 1 into, 3 into minus 1 into minus 1. Okay, 3 into, here. There is a mistake. Here we are considering gamma B. I take gamma A. So it is 1 into 7 into 1, 7. 2 into 1 into, we are considering A2, 1. So it is 2 plus 3 into minus 3, minus 9 into minus 1 is equal to 9. Okay, that is 9 plus 9, 18 by 6 is equal to 3 times. So A3 is present in 3 times, A1 is present in 0. Okay, next NE, number of times E present in gamma B. Okay, again we can write 1 by 6 into E, 1 into 7 into 2, 2 into 7, that is 14, plus 2 into minus 1, minus 2, minus 2 into 1, that is minus 2, plus 3 into minus 3 into 0, that is 0, and that is equal to 12 by 6 is equal to 2. So number of times E present in gamma B is equal to 2. Number of times A2 present in gamma B is equal to 3. Number of times A1 present in gamma B is equal to 0. So we can write gamma B is equal to A1 is not present in gamma B, but A2 present in 3 times. So 3A2 plus E present in 2 times, 2E. Okay, actually gamma B consists of 5 IR. 5 IR. Sum of, actually gamma B is a reducible representation. It is the sum of 5 irreducible representation, 3 A2 IR and 2 EIR. Okay, I think we can stop here. The direct product we can discuss in the next video. And this is very simple. Reduction of reducible representation is very simple. You have to practice this. This is very important while we are discussing the application of group theory. Reduction of a reducible representation into irreducible representation is very important. Practice yourself well. Okay. Another thing, in this case, considering NA1, NA2, that is NAI, should always be an integer. It cannot be fraction and it cannot be minus 1 because only this A1, A2, A3, etc. can be added to get the reducible representation. So it cannot be a fraction and cannot be a negative value. Can be 0. Okay. Thank you. Read the textbook well and practice it. Thank you.